All right, welcome back to your physics notes. So what we're going to focus on right now is one big, giant, useful thing that I'm going to summarize in a couple skills, and that is how to look at vectors and use them to your advantage. So remember, vectors are anything with that require two numbers to describe it. In physics, we usually show an arrow where the direction of the arrow tells you the direction, and the magnitude of the arrow tells you the length. It's very important now when you start looking at AP physics that you think about direction and dimension together, okay? So before any AP physics problem, what you're going to do is you are going to define your dimensions. So you get to pick what they are. I'm going to say the traditional way, which is up is positive y, to the right is positive x, and that's normally what we do, but I want to be very clear that you don't have to. A lot of times if it's an inclined plane problem, you wouldn't want to do it this way. You get to pick how this is, and you do it in a way that makes the problem easy to solve. Okay? So anytime you're adding vectors, whether it's velocity, force, acceleration, momentum, it doesn't matter, you add them the same way. All right? So if you have two different vectors, and they are in the same dimension, so let's call that F1, let's call that force 1, and then you have another force acting on the same object, which is F2. How would you add those together? Well, you use what's called the head-to-tail method. And what you do is you simply move those arrows so that you put them head to tail, where you draw one, that's F1, and now you take the second one and you put its tail at its head and you draw them, and you see that since they're in the same dimension, you would wind up with one long arrow. Okay? So in this case, the net force would be equal to F1 plus F2. Okay? Same dimension, it's nice and easy. Now, what if they're maybe the same dimension, but they're opposite? Okay? So I have now a new problem where I have, let's call this F1, and let's call this F2. Okay? Well, I would do the exact same thing. I would draw my first one. Let's draw it over here a little bit. That's F1. And now I would take the second one and put its tail at the head of the other one. So you can see I would start over here, and I would draw back this way. Okay? So here's F1. Here's F2 going back this way. And you see that this section right here, they cancel each other out. And that is what is left over. Okay? So that is my net force, and in this case, you can see that what you would do mathematically for the magnitude, you would take F2 minus F1. Okay? Now, you don't have to do it this way. You can just look at the numbers, but the arrows make it very easy to keep track of what should be positive, what should be negative, what you subtract, what you add, etc. Now, you can also do the head-to-tail method if they're in two dimensions. So let's say I have a vector F1 that goes up. I have another vector F2 that goes like that, and maybe I have another vector F3 that goes like that. I would do the exact same thing. I would take F1, draw it, take head-to-tail method, F2 right there, and now F3 right there. You can transfer F3 over here and cancel those out if you want to, but you can see that what's important is the net vector is what points from there to there. So this would be your net vector. Okay? That's one way of doing it. Now, that doesn't really help you too much in getting an answer unless you think about it, okay? So if I look at my positive y and negative y values, I could get a vector in the y dimension. So f in the y dimension is going to be equal to f1, which is positive, plus negative or minus f3, which is in the negative dimension, okay? Now, f in the x dimension, there's only one of them, so that's equal to f2. So what I would get is I would have a triangle. You can see that it's kind of a triangle right here, but I would have a triangle with an x value of f2, and I would have a y value of f1 minus f3. And what I would want to find is the hypotenuse of that, which you would use Pythagorean theorem to do so. Okay? Now, the other way to do it is if I give you a vector that is already in two dimensions. So let's say I tell you this is your vector. Let's just call it f. And that vector is at an angle, theta, from the horizontal. Okay? It becomes very useful to take this and transfer it from this complicated form where it's acting in 2 dimensions to a significantly simple form where it has maybe one vector that's y and one vector that's x. Since these vectors can combine to form a 2-dimensional vector, you can do the opposite, and you can take a 2-dimensional vector and break it down into its x and y components. To do that, you think of a little trigonometry, you make a right triangle, okay? These 2 dotted lines that I drew are equivalent to that line that's straight, okay? If you have a force that applies in that direction with that magnitude, and you compare that to a different force that goes to the right with this magnitude and a force that goes up with that magnitude, you would have the exact same result. So to do this, you think back to your trigonometry. You might remember SOHCAHTOA. If you don't and you need some help with this, that's fine. You can come and ask me. But effectively, SOHCAHTOA translates to sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And I remember this as some old hippie caught another hippie tripping on apple juice. Or, well, it's actually supposed to be acid, but I don't know if I'm supposed to say that. Anyway, so that's your trigonometry terms. You don't really have to get much deeper into that if trigonometry bothers you. But looking at this right here, this y component, is opposite the angle. Okay? So if I'm looking to find, let's say, the y value, I would need to pick one of these 3 sets of terms that would have what I know. Well, I know that the hypotenuse is f and the angle is theta, okay? So this is sine theta, cosine theta, tangent theta, right? And so I know 2, I need the third one to be the opposite. So let's, right here, I know that sine theta, because I know what theta is, and sine is just a ratio. Opposite is what I'm looking for, hypotenuse is f. So I know that, right? So I can write sine theta equals opposite, which is whatever f sub y is, that's my force in the y dimension, divided by hypotenuse, which is f, okay? And now I need to solve for fy. So you just do some algebra, and you rearrange that equation, you move the f over, and you get f sine theta. So this right here is f sine theta, okay? Now what do I do for down here? The same thing, but now I have more choices. If I go with the same logic I had before, I know the hypotenuse, I know what theta is, so I can pick cosine theta because I'm looking for the adjacent side. So cosine theta equals adjacent, which is going to be f in the x dimension over hypotenuse. And now I just solve for that. So f of x equals cosine theta. Sorry, f cosine theta. So now what I've done is I've broken this 2-dimensional vector down into a vector that acts in 1 dimension, the x dimension, and an additional one that acts in the y dimension. That might seem kind of not very useful right now, but if you were doing, let's say, a force table problem where you had a ring and you had a force that was acting in that direction, F1, you had another force that was acting in that direction, F2, and you had a third force that was acting in that direction, F3. When you did this with 2 forces, everyone was very clear that they had to be 180 degrees apart and they had to be equal because they cancel each other out. Well, now what you could do is you could break down each of these vectors into their components. And I would challenge you to conceptually think about what the magnitude of those 2 have to be and what the combined magnitude of their x values have to be. But so this is a very useful tool. Forces, I think, is the easiest way to start to understand vectors, which is why we start with it. All right, so there you go. Vectors and forces. Good luck.